Okay, so in this section, we're going to be investigating improper integrals. And so the first thing is we need to know when is an integral considered improper? Well, it's going to be considered improper if one of these two things happens. Either A, we have infinite limits, or B, we have something where we have a point in our interval that's undefined. What I mean by that, so when I say infinite limits, I mean that either we have infinity as our top limit, negative infinity as our bottom limit, or we could even have both of them. And so we'll look at what do we do in each of these three cases? How do we handle this? By having points where it's undefined, what I mean is that we have some integral a to b of f of x dx. And this a and or b, they could be infinite, right? In which case we would have a combination of case 2 and case 1. But basically what we're saying is that inside this interval AB, there's some x value, right? So x is greater than or equal to a, less than or equal to b. There's some x value in here such that f of x does not exist. An example of this would be something like the integral from negative 2 to 2 of x inverse dx, and that's because 1 over 0 is undefined. So let's start by looking at case 1. Whenever you have positive or negative infinity as one or both of the limits, we'll rewrite our integral using one of the three following things. Note that for now, I'm going to assume f of x is continuous within the interval that we're integrating over. Okay? So I'm not going to involve case 2 yet. So if we're trying to integrate something that looks like this, where we have, our bottom limit is some number a, and our upper limit is infinity, what we're going to do is we're going to rewrite this as the limit as t goes to infinity, and then we're going to replace this infinity with t. Right? So that kind of means like we're calculating, let's say we have something like the integral from 1 to infinity of f of x dx. Then we're calculating like the integral from 1 to 2 of f of x dx, 1 to 200, f of x dx, and so on, right? Just letting this upper limit get bigger and bigger and bigger to see what this answer is going off to, right? And so one way for us to do that is replacing this infinity with a t, calculating, right? So when we do this, we're still going to be calculating some, right? So let's take an example. Let's just take the integral of 1 dx from a to t. I'm not even going to worry about the limit right now. I just want to tell you that like this works the exact same as when we just have actual numbers in here, right? So this would be the integral of 1 is x, and then evaluated from a to t. So then this would be equal to just t minus a, right? We're going to have a lot more complicated integrals, and then we'd have to do a limit as t goes to infinity of whatever this expression is. But this is kind of how it will work. Now, if it's flipped, if we have negative infinity on bottom, sorry, this should say, there should be an f of x dx in here. Whenever we have a negative infinity on bottom, then we write limit as t goes to negative infinity, and then replace that negative infinity in our integral with a t. Now, if you're trying to integrate something where we're going from negative infinity to infinity, you're going to break this up, right? So we have this interval, right? Negative infinity to infinity. And this is going to be equal to negative infinity to a union a to infinity. And so what it is we just pick some number a to kind of cut this interval into two halves. Right, so imagine we've got a number line, and this is like negative infinity, infinity, and then maybe I choose like a equals 0. And so I'm kind of evaluating one integral over here, right? So maybe that's this integral, and then another integral over here. Often we will use a equals 0 just because it's a really nice thing for us to plug in when we're trying to evaluate. So let's look at an example. Here we have the integral from 1 to infinity of 1 over square root x dx. So our very first step is to rewrite this as the limit as t goes to infinity. Then we'll have the integral from 1 to t of 1 over square root x. That's the same thing as x to the negative 1/2 dx. So now I'm just going to, we don't even mess with this limit until we get to the end of the problem, usually. So I'm just worried about calculating my integral right now. Well, I know that this is just going to be power rule. So I add 1 to the exponent, I get x to the 1/2, and then I divide by 1/2. So I get 2x to the 1/2 evaluated from 1 to t. And so this gives me the limit as t goes to infinity of 2 t to the 1/2 minus 2 times 1 to the 1/2, so it'll just be 2 times 1, which is 2. Now this is something similar to what you would have seen in Math 151 or Cal 1, where you have to evaluate limits. So what we get here is essentially if t is going to infinity, then this is 2 square root infinity minus 2. The square root of infinity, well, that's still going to be going to infinity. And so we'll have, 2 times infinity minus 2, which is just going to be infinity. And so in this case, we say that the integral diverges to positive infinity. Okay, now let's look at our next example. So similarly here, I start by rewriting this as a limit. So this is the limit as t goes to infinity. The integral from 3 to infinity of 1 over x dx. Okay, so then this is the limit as t goes to infinity. So the integral of 1 over x is natural log absolute value x, and we're evaluating from 3 to infinity. By the way, we're dealing with some fairly simple limits right now, but it'd be a really good idea if you have forgotten L'Hopital's rule and other limit tricks to go back and review that stuff from Math 151 or from Calculus 1. If you need some help for locating those resources, please reach out to me and I will get you those resources. So then this becomes the limit, this infinity should have been a t. So then this becomes the limit as t goes to infinity of ln of, what I notice about this interval here, right, this is the interval from 3 to t, and t is going off to infinity. These are all going to be positive numbers, so I'm not worried about this absolute value sign. Okay, so this is going to be ln of t minus ln of 3. So this is the limit as t goes to infinity of ln of t over 3 using our log rules. So then this is ln infinity over 3. So this is the natural log of infinity, which is just going to be infinity. And so again, in this case, we say this diverges to infinity. Now I'm leaving example 3 as a practice problem. Just like we had practice problems in the previous lecture, I will upload the work onto this problem. But this is a good way to test yourself that You can follow from example 1 and example 2 to complete example 3. And then you may start noticing a pattern. If you have it, here's an important thing. This is highly important. It's going to cut down on a lot of work. It's called the p-test. And it says that if you have a greater than 0, right? So we have the integral from a to infinity. A is some number. If that number is greater than 0, then 1 over x to the p will converge if p is greater than 1. And it will diverge if p is less than or equal to 1. So let's go back and look at these cases. This is 1 over x squared. Our a is bigger than 0, so we can use the p-test. By the p-test, we automatically know this converges without doing any work at all. Similarly here, I had 1 over x to the 1. Now let's scroll back down and look at our p-test. 1 is less than or equal to 1, so we use this rule saying that it will diverge, which is exactly what we got. Then let's look here. This was 1 over square root x, so that's x to the 1/2. Again, our a is positive, so we have 1 over x to the 1/2. The p-test automatically tells us that that diverges. Right, so the p-test isn't going to tell you what it diverges or converges to, but there are times where we're only interested in, does this thing converge or does this thing diverge? And just as a reminder, when we're looking at integrals like this, so here's an example. If I take, let's take this graph of 1 over x, for example. What this looks like is something like this. Or we have a vertical asymptote here and a horizontal asymptote here. And so if this is, say, 3 right here, then what we're calculating here is the area of this region. Right? And so this never touches the x-axis, so we're calculating this all the way off to infinity. And so basically what we determine by this is that the area of this region is actually infinite. And so we might be, what's the word? We might think that, okay, well, it goes on forever, so of course the area has to be infinite. But there are times where we're going to learn that that is very much not the case. Right? So, for example, here, when we do the integral from 1 to infinity of 1 over x squared, yeah, that interval that we're integrating over goes on forever. And so our region is going off to infinity. But it turns out that it approaches the x-axis fast enough to where we actually get a finite answer. So that's kind of just a picture of what's going on. Alright, let's look at example 4. This is a great time for us to combine a couple of things in one problem. So the first thing that we're going to use is what we just learned, which is how to rewrite this using limits. So this is going to be the limit as t goes to infinity of the integral from 0 to t of x squared e to the negative x cubed dx. Now what I'm going to do is I'm going to use a u substitution. So u will be equal to negative x cubed, which means that du over negative 3x squared is equal to dx. Now, when we plug back in our u substitution, we need to be careful. The one thing that a lot of people are going to miss, and it's going to be really infuriating to all of us, is that we're going to forget to change our limits of integration. We need to plug this t in for x in our u formula. So this is going to become negative t cubed. This will be negative 0 cubed, which is just 0. I'll write this a little bit better. We should have x squared e to the u over negative 3x squared du. Now this inside of our integral is being multiplied by negative 1/3. What we usually do is we pass that outside the integral. We can pass it all the way outside of our limit. Whenever you have continuous functions with a limit, you can move that limit around. Right, so if I'm taking limit as t goes to infinity of e to the x, I can rewrite that as e to the limit as t goes to infinity of x, because e to the x is a continuous function, so I can move my limit around. So when we rewrite this, we should have negative 1/3 limit as t goes to infinity of, so we'll keep this. Our limits of integration stay the same. We cancel out these x squareds and we're left with e to the u du. So this is negative 1/3 limit t goes to infinity of, now I plug in for u. Well, so the integral of e to the u is just e to the u. And so this becomes e to the u, and we're evaluating from 0 to negative t cubed. And so this becomes negative 1/3 times the limit as t goes to infinity of e to the negative t cubed minus e to the 0. So this is negative 1/3 times, now I'm going to plug in t for infinity. So this is going to be e to the negative infinity cubed, which is just going to be negative infinity, minus 1. And so what we should notice is that if we take e to the negative infinity, that's going to go to 0. And so this becomes 0 minus 1. Multiplying out our negative 1/3, we will get a positive 1/3. So this tells us that our integral converges to 1/3. Okay. Now looking at example 5, this we need to go ahead and rewrite it as a limit. So we've got the limit as t goes to infinity of 6 to t, and this is 1 over x squared minus 7x plus 12. And this we should recognize as a time to do partial fractions. So first thing I'm going to do is I'm going to take that quadratic on the bottom and factor it, so it becomes x minus 3, x minus 4, equals a over x minus 3 plus b over x minus 4. And so I'd like you to go ahead and pause the video now and solve for a and b. Now that you've solved for a and b, you should have a equals negative 1 and b equals 1. If you don't, then come meet me in office hours and we can talk about this. I'm going to separate this. Okay. So now I can rewrite my integral again. So this is still 6 to t. And then I should have negative 1 over x minus 3 plus 1 over x minus 4 dx. So this is the limit as t goes to infinity. And now I'm going to go ahead and integrate this. So negative 1 over x minus 3, that would be negative natural log absolute value x minus 3 plus natural log absolute value x minus 4 from 6 to t. So then this becomes the limit as t goes to infinity So I'll plug in t for x. And again, so we're not too concerned about absolute value signs here. I put them in there just because I want you to remember that it is absolute value. But since our interval is from 6 to t, which is 6 to infinity, we're just going to have positive numbers that are bigger than 4, so we don't have to be concerned about having negatives inside our absolute value. So this becomes... Actually, before we start evaluating, I'm going to use our natural log rules to rewrite this as the natural log of x minus 4 divided by x minus 3. And that's because of this negative sign right there. Evaluated from t to 6. So then this is the limit as t goes to infinity of ln of t minus 4 over t minus 3 minus ln 2 over 3. And I get that from plugging in 6 for x. Now by L'Hopital's rule, we can move, so this doesn't have a t in it. It's not getting affected. So all I'm really trying to calculate is the limit as t goes to infinity ln t minus 4 over t minus 3 minus ln 2/3. So the point here is that I can move this limit inside my natural log, because the natural log is going to be a continuous function over our interval. Right, as we're going to infinity, it's continuous, so we're good. So then this is the natural log limit as t goes to infinity of t minus 4 over t minus 3 minus ln 2/3. Using L'Hopital's rule on this inside, that's where we take the derivative of the numerator, derivative of the denominator. This will just give us ln of 1, because we'll get 1 over 1 after taking our derivative, minus ln 2/3. And this is a good time to remember that the natural log of 1 is equal to 0. So this is 0 minus ln 2/3. And so then this tells me that our integral is going to converge to negative ln of 2/3. If I use our natural log rules, we have a negative 1 inside that exponent, or in front of our ln, so I can move that to the exponent. If we have 2/3 to the negative 1, that becomes ln 3/2. Now, for example 6, this will be a great time to practice integration by parts. So for integration by parts, first I need to rewrite this as a limit. And so this is a little bit different because now we don't have our infinity up top, which means now I'm doing the limit as t goes to negative infinity of x e to the x, of the integral from 0, or from t to 0, of x e to the x dx. So I'm going to go ahead and use our table method. So we have u v prime, x will be our u, v prime will be e to the x. So then this is 1 and e to the x, 0 and e to the x. And then we need our signs. So this is plus, minus. And so this becomes limit as t goes to negative infinity of, let's see, we'll have x e to the x minus e to the x evaluated from t to 0. So this is limit as t goes to negative infinity. Plugging in 0, I'll get 0 times e to the 0 minus e to the 0 minus, now I'll plug in t. So this is t e to the t minus e to the t. Now I'm going to let t run off to negative infinity. So this becomes 0 minus 1 minus, we'll have negative infinity times e to the negative infinity minus e to the negative infinity. So this is negative 1 minus, let's see, negative infinity times e to the negative infinity. Well, e to the negative infinity is 0, so this is negative infinity times 0, which is 0, minus e to the negative infinity is 0, so we should get zeros inside here. And so our answer is negative 1. And so that tells me that our integral converges to negative 1. So that means that the area under the curve of this function from negative infinity to 0, even though, right, we consider area to be positive, that just means that our net area taken the amount above and below the x-axis is going to be equal to negative 1. Okay, and then here's a quote-unquote, I guess, fun situation where we're not going from a constant to infinity or negative infinity to a constant. Here we actually have two infinities, and we'll have a different way of evaluating this integral. So here, noticing that inside this integral it looks like 1 over x squared plus a squared, we know we're probably going to be using our arctan rule for integrals. And so when I think about taking arctan, what I really like taking arctan of is 0. Because I know arctan of 0 is 0. So it's a nice thing to evaluate. So what I'm going to do is I'm going to split this integral up at 0. So this is going to be the integral from negative infinity to 0 of dx over x squared plus 4 plus the integral from 0 to infinity dx over x squared plus 4. And so this becomes the limit as t goes to negative infinity, integral from t to 0 dx over x squared plus 4, plus, now I need a new variable. The variable I'm going to use now is going to be z. So z goes to infinity, integral from 0 to z of dx over x squared plus 4. So this becomes the limit as t goes to negative infinity of, right, so this should be 1 over a, our a is 2, so 1/2, arctan x over a, so x over 2, evaluated from t to 0, plus limit as z goes to infinity. We'll have the same thing, except for this is going to go from 0 to z. Okay, now we can start looking at evaluating this. So this is the limit as t goes to negative infinity. So when I plug in 0, I'm going to get arctan of 0 over 2. So it's arctan of 0, which is 0. So plugging in 0, we just get 0. That's why I chose this as our split point, because it's really nice to plug in here. And then we would so we'd have 0 minus, now we're plugging in t, so this is going to be 1/2 arctan t over 2 plus, I should have limit as z goes to infinity. Similarly, over here, I'll have 1/2 arctan z over 2 minus 0. Okay, so this is kind of like saying, let's see, we'll have negative 1/2 arctan. T's going to negative infinity, so this is negative infinity over 2, which is just negative infinity. Plus, now I should have 1/2 arctan. Z's going to infinity, so this is infinity over 2, which is just infinity. Now what I want to do is I want to think about the arctan graph real quick. The arctan graph looks something like this. This is at pi over 2. This is at negative pi over 2. These are vertical asymptotes. Maybe not perfect, but it looks somewhat like this. So we can see as our y value is going to negative infinity, or sorry, this isn't the arctan graph, this is the tan graph. So when we're looking at our y value going to negative infinity, because this represents our y value in here, we can see that our x value is going to negative pi over 2. So this is negative 1/2 times negative pi over 2 plus 1/2 arctan of infinity. So as our y value is going to infinity, here our x value is approaching pi over 2. So times pi over 2. So this is negative 1 times negative pi, which gives us positive pi over 4 plus pi over 4, which gives us 2 pi over 4, which is equal to pi over 2. So that tells me that our integral converges to pi over 2. Alright, at this point, I want you to go ahead and stop, congratulate yourself for all the work you've done this week, and take a break. You've now covered all the material that you need to cover in order to be ready for Wednesday's class material. If you want to keep going, feel free to keep going, but we won't be covering case 2 in Wednesday's class material. There are, I believe, let's see. Here's a practice problem. Okay, yeah. No, so, yeah, you're good. There won't be anything in the rest of this that's kind of like more practice over case 1. Everything that comes after will either be included in what we call the comparison theorem, or it'll be included in this case 2. Alright, now for case 2, the way this works is that we're going to have some discontinuity in our function that we're integrating. For example, here, our issue would be if we're dividing by 0, which would only happen if x minus 9 equals 0. Well, that happens precisely at x equals 9, which is in our interval. So what we need to do is we need to take an integral from t to 36, where t is going to be numbers within our integral that get closer and closer to 9. What I mean by that is, picture we have a number line. Here's 36, here's 0, here's 9. This is where our discontinuity is, right? This is a bad point. So what I want to do is I want to take t values closer and closer to 9, but not actually touching 9, right? I'm taking a limit as we approach 9. And it's very important that we note that we're approaching 9 from the right-hand side. So once we have that, we can rewrite our integral as limit as t approaches 9 from the right of the integral from t to 36 of, let's see, this is x minus 9 to the negative 1/3 dx. So then this becomes the limit as t approaches 9 from the right. I can go ahead and integrate this. This would give me x minus 9, add 1 to the exponent, so it becomes 2/3, multiplied by the reciprocal, and then evaluate from t to 36. So this is the limit as t approaches 9 from the right. I'm going to pull out this 3/2. And in fact, like I was saying in the previous lecture video, we can pull this out in front of the limit of, let's see, we should have 36 minus 9, which is 27, to the 2/3, whoops, minus t minus 9 to the 2/3. So this is going to be 3/2 times, okay, so 27 to the 2/3, there's no t there, so I don't have to worry about my limit. This is going to be the cube root of 27 squared. Well, the cube root of 27 is 3, and then 3 squared will give us 9. Minus, now we have a t. This t is going to be approaching 9 from the right. So we're going to be looking at what happens as our t values are something like 10, 9.5, 9.1, 9.01, on and on and on. Well, as I'm plugging those numbers in here, we're going to be approaching 0. So we'll have 0 to the 2/3, which is just 0. And so this will give us 27 over 2. And so that tells us that our integral converges to 27 over 2. Let's take another example. A lot of our examples where we have issues is taking the natural log of something that's less than 1, or dividing by 0, or taking square roots of negative numbers. That's where a lot of our issues are going to come from when we're checking for discontinuities. So here I notice that an issue would be if 4x minus 5 is equal to 0. So this would mean that 4x equals 5, which means that x equals 5/4, and unfortunately that is in our interval. So again, if we look at a number line, if I'm going from 0 to 5/4, and this is my problem, right? At x equals 5/4 is where we have a discontinuity. Then I want to get infinitely close to it but not touch it. And so I'm going to be approaching it from the left-hand side. So it tells me that this is the limit as t approaches 5/4 from the left of the integral from 0 to t of 1 over 4x minus 5 dx. Now I'm going to use a little bit of u substitution here. So I'll use u equals 4x minus 5, which means that du over 4 equals dx. So this becomes, and I'm going to get rid of this so we don't get confused anywhere, the limit as t approaches 5/4 from the left, integral. Now I have to be careful here, we're doing a u sub, so I need to change my limits. So this will be -5, this will be 4t minus 5, right? I'm plugging 0 and t in for x in this equation. And so then I get 1 over u times du over 4. I'll go ahead and pull that 1/4 in front of our limit. So this is 1/4 limit as t approaches 5/4 from the left. So now I just have the integral of 1 over u du. So this is natural log of absolute value of u from -5 to 4t minus 5. And so this is super important because we're taking a absolute value here. All right. So this is going to be 1/4 times limit as t approaches 5/4 from the left of natural log of, so I'll plug in 4t minus 5, so this is absolute value 4t minus 5, minus natural log of absolute value -5. Alright, so this will give us 1/4 times, so moving our limit inside the natural log here, this part is going to be going to 0, and we'll have negative numbers, but it's okay because we have our absolute value. So this would be like saying natural log of 0. So this means that we're going towards negative infinity. So we'll have negative infinity minus ln of 5, which is just some constant number. And so this is just going to be negative infinity. If some of these limits are tripping you up, then please do not hesitate to reach out to me. That way we can go over limits. Limits are a huge part of these improper integrals. In fact, really, other than setting up what our limit should look like, as in like how do we split up this integral, are we coming from the left or the right side? Other than that, I'd say that finding the limit is actually probably the hardest part of these problems. And I think the only reason it's so difficult is because we just haven't used that stuff in a while. I'm going to leave example 10 as a practice problem. This will be a great time to use our improper integrals because we can't take the natural log of 0. And it'll be a good time to use our integration by parts when we integrate ln of x. And just a little note, sorry for killing trees, but I couldn't put example 11 on page 6 because example 11 just takes quite a bit of room, to say the least. Okay, the first thing I'm going to notice is that we have negative infinity to infinity, which is a problem. The second thing I'm going to notice is that even if I rewrite this, so I'm going to keep the limits the same, when I factor the bottom, this is x plus 3 times x minus 2. Which means not only do we have infinite limits, we also have an issue that we have discontinuities at x equals -3 and x equals 2. So we need to rewrite this as the limit as we're going to have t going to, let's see, actually let's just, for now, let me just break up this integral into its separate parts. Meaning I want to go from negative infinity to our first discontinuity, then from that discontinuity to the second discontinuity, from that second discontinuity to infinity. Okay, so we're going from negative infinity to our first discontinuity, which is x equals -3. So 1 over x plus 3, x minus 2, dx, plus the integral from -3 to 2, 1 over x plus 3, x minus 2 dx, plus the integral from 2 to infinity of 1 over x plus 3, x minus 2 dx. Now here's the thing. If we can get that just one of these integrals diverge, then the entire thing is going to be divergent. We're not going to have to worry about adding infinities to cancel out and make 0 or anything like that. If we get that something diverges to positive or negative infinity, then we're going to, for our purposes, say that our integral diverges. Okay? And so that's what I want to know here. Does it diverge or does it converge to some particular number? In order for it to converge to some particular number, we're going to have that each of these three pieces converges. Before we do anything like that, I want to notice that this is going to be a time for us to employ our partial fractions technique. So we'll have 1 over x plus 3, x minus 2 is equal to a over x plus 3 plus b over x minus 2. Let me go ahead and split this up. And actually, let me go ahead and use a different color over here. So then we get 1 equals a times x minus 2 plus b times x plus 3. So 1 equals ax minus 2a plus bx plus 3b. So 1 equals x, a plus b, plus negative 2a plus 3b. And so this will tell me that a plus b equals 0, which means a equals negative b, and negative 2a plus 3b must be equal to 1. So plugging in a equals negative b, this will become 2b plus 3b equals 1. So 5b equals 1 means that b equals 1/5. So a must be equal to negative 1/5. Alright, what I'm going to do is I'm going to go ahead and label these. We're going to call this portion integral 1, this portion integral 2, this portion integral 3. My hope is that I evaluate one of these and that it is going to diverge. Okay, so the way we're going to do this is for this first portion, we'll have a limit. I'll have t going to negative infinity, and I'm going to have z going to negative 3 from the left-hand side. Right? Because we're coming from negative infinity to 3, so I'm coming from like negative 10, negative 7, negative 5, negative 4. Right? We're approaching it from the left-hand side. This is going to be of, so I should have the integral from t to z of negative 1/5, negative 1/5 divided by x plus 3 plus 1/5 divided by x minus 2. Where I'm getting this from is from our a over x plus 3 plus b over x minus 2, and then plugging in the solutions that we got for a and b. So keep our limit the same. We have t going to negative infinity, z going to negative 3 from the left, and so we'll have, taking the integral, we should have negative 1/5 ln x plus 3 plus, put our brackets around it. Ln, sorry, 1/5 ln x minus 2. And the thing I'm missing here is that when we integrate, we should have absolute value. And this is going from t to z. Okay. So then this becomes limit as t goes to negative infinity, z goes to negative 3 of, let's see, we'll have negative 1/5 ln absolute value z plus 3 plus 1/5 ln absolute value z minus 2 minus, I should have negative 1/5 ln absolute value t plus 3, and of course I'll run out of room. Plus 1/5 ln absolute value t minus 2. Now what I'm going to do to make this a little bit easier is pull out a factor of 1/5. So this is 1/5, oh my gosh, 1/5 times the limit as t goes to negative infinity, z goes to negative 3, of, so let's see, I should have natural log absolute value up. We need a negative sign in front. That's that negative 1/5. We only factored out 1/5, not negative 1/5. Absolute value z plus 3 plus ln absolute value z minus 2. So now I'm going to distribute my negative, so we'll have plus 1/5 ln absolute value t plus 3 plus, minus 1/5 ln absolute value t minus 2. Now we'll use our natural log rules to rewrite this. I'm sorry about this. We pulled out the 1/5, so I should not have 1/5 in there. And so this becomes the natural log of the absolute value of z minus 2 over z plus 3 plus the natural log of the absolute value of t plus 3 over t minus 2. Okay, so this becomes 1/5 times, now remember we can move our infinite limit inside our natural log. And we can even move our limit as z goes to negative 3 inside our natural log. So this is going to be ln absolute value limit as z goes to negative 3. I don't have to be concerned about the t here because I don't have any t's. Of z minus 2 over z plus 3 plus natural log absolute value limit as t goes to negative infinity of t plus 3 over t minus 2 Alright, let's start evaluating some of this stuff. So I have z going to negative 3, which means that this denominator is going to 0. So this is either going to positive or negative infinity. Well, the thing I'm missing is that we were going to... This is where this comes into play. This from the left-hand side. I need to carry this on throughout the problem. Okay, so we're approaching from the left-hand side, which means I'm plugging in stuff like -5, -4, -4.5. So that means the numbers on the bottom of this fraction are going to be negative. And the numbers on the top of our fraction are going to be negative. So we have a negative over a negative, which means we have a positive. So this is positive infinity. Plus ln. Here we can use L'Hopital's rule. So this is just going to be absolute value of 1. So this will give us 1/5 times infinity plus 0, which will give us infinity. And so we are done because we got that this one integral out of our 3 diverged, which means the entire thing has to diverge. So the integral diverges. Okay. Moving on from there, now we are done with looking at these ridiculous improper integrals, and we're going to start looking at something called the comparison theorem. So the comparison theorem is just for deciding if something converges or diverges. In order to use it, first of all, we need to be integrating functions that are continuous over the interval that we're looking at. Second of all, we need something that goes from a to infinity, with a being greater than or equal to 0. Okay. So what we need is if the integral from a to infinity of f of x is convergent, then the integral from a to infinity of g of x will be convergent if g of x is smaller than f of x. So what we assume is that f of x and g of x are going to be continuous functions, and g of x is going to be strictly less than f of x, but it's also going to be greater than or equal to 0 for all x in our interval from a to infinity. Another way of saying this is that if you have if you're comparing two integrals, right, the integral of f of x and the integral of g of x, both on the interval from a to infinity, if the bigger function converges, then so does the smaller function. Right, so if I have something, right, let's say that our f of x is green, and it looks something like this, right? And let's say that this area under the curve, right, this is our integral from a to infinity. Let's say that this area is represented by some number. It's not infinite. Then if I take some g of x, which I'm going to represent with a blue curve, and it's always less than f of x but still positive, that means its area, the area under the curve of the blue curve, has to be smaller than the area under the curve of the green curve. So if the green curve converges, then the blue curve has to also converge. Alright, that's what I mean by if the bigger function converges, then so does the smaller function. And the opposite is also going to work. If we have some smaller function that diverges, then so does the bigger function. So when you're using the comparison theorem, you either need to find a continuous comparison function that is bigger and converges, or you need to find a continuous comparison function that is smaller and diverges. So let's walk through the steps of how to use this. The first thing is that we verify that our function is continuous in the interval of the given integral. So what I mean by that, so our interval here is going to be 1 to infinity. And this is, I'm sorry, I'm just like kind of like stuttering all over the place, but it is a real tongue twister to be saying interval and integral so close to each other and just like all over the place. It's one of those things like try to say it 10 times fast or something like that. Okay, so we're in the interval of 1 to infinity. Well, 1's a constant, that's continuous. E to the negative x is continuous everywhere. An issue would be if we were dividing by 0. But 0 isn't in this interval. So we're good. Our f of x is continuous. Right. So this is our first thing to check. Is the function continuous in our interval? Right, and we want our interval to be from a to infinity, where a is a positive number. Which we have that our a here would be 1. Now we want to pick a continuous function that is always greater than f of x, and it converges. Or we want to pick a function that is always smaller than it, and it diverges. So let's see how we do that. So this was step 1. Now let's look at step 2. The best way to do step 2 is to focus on either the numerator or the denominator. I like to focus on the more complicated thing. Just seems more fun, right? So I'm going to look at 1 plus e to the negative x and figure out, okay, what do I know about this thing? Well, I know that this is the same thing as 1 plus 1 over e to the x. Okay, now I want to look at how do fractions work. So if I have something like 1/3, what is its comparison to 1/2? We should know that 1/3 is less than 1/2. And so what's happened here is I kept the numerator the same. All I did was I adjusted the denominator. So if you have a fraction, and I'm ignoring negative values for now, but if you have a fraction and you make your denominator smaller, right, we put it closer to 0, then you're going to be making the new fraction bigger, right? So I took 3, I made it smaller, I chose a smaller number, which was 2, and that makes my new fraction bigger. So I'm going to write this down, because this is very important for this section. Bigger denominator means smaller fraction. Also, smaller denominator means bigger fraction. Right, so this is saying if I keep my numerator the same and I make the denominator bigger, then I get a smaller fraction. I get a smaller number, right? So for example, let's look at 1/4. Well, 1/4 is less than 1/3. So I just made this denominator bigger. I went from 3 to 4, and so my number gets smaller. Now, why is that important? What I want to look at is what's the comparison between 1 over e to the x and then just 1 over 1. Well, we know that x is greater than or equal to 1. So that means that the smallest e to the x can be is e to the 1. And e is approximately 2.7. So what I've done here is I kept the numerator the same. My denominator has now gotten smaller, which means this must be bigger. Okay, so then this means that 1 plus 1 over e to the x is less than or equal to, strictly less than let's do less than or equal to. Less than or equal to 1 plus 1 over e, right? Because we said the smallest that x can be is 1. And then this is going to be strictly less than 1 plus 1 over 1, which is equal to 2. So what I've gotten is I've gotten something that is bigger than 1 plus 1 over e to the x. And it's going to be bigger than that for all x values. Why is this important? Well, this means that 1 plus e to the negative x over x is strictly less than 2 over x. So what I've done is I've found a bigger comparison function. So this is my g of x. And this is okay to choose because it's going to be continuous in our interval from 1 to infinity. Okay, so then the third thing to do is to look at the integral of this over our interval. So let me write this down. Since we have a bigger function, we want our integral to converge. Because remember, our rules say that we either want a continuous function that is always greater than the given function and converges, right? So we found something that's always greater, so we need it to converge. So let's look at the integral from 1 to infinity of 2 over x dx. This is 2 times the integral from 1 to infinity of 1 over x dx. And from the p-test, we know that this diverges. This means that we did not choose an acceptable comparison function, right? We either chose something that was too big, or we should have been looking for something that was smaller. So let's try redoing step 2. This time, instead of trying to find something bigger, I want to find something that's smaller. Okay, so 1 plus e to the negative x. This is 1 plus 1 over e to the x. So I want something that's always going to be smaller than this. Well, notice that this 1 over e to the x, this is always going to be some positive value. It's always going to be greater than 0. So we know that 1 over e to the x is always greater than 0. This means that 1 plus 1 over e to the x is greater than 1 plus 0, which is just 1. Okay. So then this means that 1 plus e to the negative x over x is always going to be greater than 1 over x. Awesome. Let's look at step 3, which is to integrate this guy. Right, to integrate our new comparison function. Now, we got something that's smaller. So since we got something that's smaller, we want our integral to diverge. So this is like the bread and butter of the theorem. If you get something bigger, you want it to converge. If you get something smaller, you want it to diverge. This is super important. You have got to know this part of the theorem, right? Yes, it's important to verify that these are continuous. Yes, it's important that our interval goes from a to infinity where a is greater than 0. But this part in here is the part that people most often forget. Okay, so let's look at the integral from 1 to infinity of 1 over x dx? Well, the p-test already tells us that this diverges. This is the importance of memorizing the p-test. I did absolutely no math right there in calculating that. All I know is the p-test, which says that it diverges. Now, okay, there's math in developing the p-test and stuff, so I guess technically we're doing math. But more than anything, we're just stating something that we know is true without having to actually integrate this. We can integrate this. We can use our method of improper integrals, calculate the limit and all that stuff, and we'll get that it diverges. But this is such a time saver right here. So what we say at the end of this is that by the comparison theorem on integral from 1 to infinity of 1 over x dx, our integral must diverge. Our integral diverges. Now let's try this again. So I have this example, and the first thing I notice is that we have e to the negative x squared, which is going to be continuous everywhere, so continuity isn't an issue here. What is an issue is that our a value is 0. We need it to be greater than or equal to 0. So what I'm going to note is that the integral from 0 to infinity of e to the negative x squared dx is equal to the integral from 0 to 1 e to the negative x squared dx plus the integral from 1 to infinity of e to the negative x squared dx. I know that this part converges. I know that for a fact because 0 to 1 is a bounded interval, and e to the negative x squared doesn't have any vertical asymptotes in there. So this has to be some finite amount of area. What I don't know about is this part right here, because 1 to infinity is an unbounded interval, so this could possibly give us an infinite amount of area. So this is the part that we're interested in using the comparison theorem on. And we can use it now because now we have an a value of 1, which is bigger than 0. So let's see. Step 1. E to the negative x squared is continuous everywhere. Step 2. We need to find a comparison function. Alright, now what I want to notice is that our interval is from 1 to infinity. So our interval is 1 to infinity. Because of this, we can say that x squared is always greater than or equal to x. And most people might be saying, okay, well that's true no matter what our interval is. Okay, but there's some cases like if we plug in 0.5, then the left would be 0.5 squared, which is 0.25. And then the right hand side would be 0.5. So we can't say that 0.25 is greater than or equal to 0.5. Right, so fractions will give us issues here. But numbers ranging from 1 to infinity will not give us issues here. So this means that this means that if I multiply by a negative on both sides, we still get negative x squared is... So now, the important thing here is if I'm going to multiply by a negative on both sides, when we multiply by a negative, our inequality sign has to flip. So we have that negative x squared would be less than or equal to negative x. Which means that e to the negative x squared is less than or equal to e to the negative x. Which means that the integral from 1 to infinity of e to the negative x squared is strictly less than the integral from 1 to infinity of e to the negative x, to the negative x dx. So what we want, we found something that's bigger, so we want it to converge. So we want convergence. Alright, so let's go ahead and calculate our integral. So we're calculating the integral from 1 to infinity of e to the negative x dx. Well, that's going to be the limit as t goes to infinity. Integral 1 to t of e to the negative x dx. So this is the limit as t goes to infinity of negative e to the negative x from 1 to t. So then this is the limit as t goes to infinity of negative e to the negative t minus negative e to the negative 1. So this becomes, let's see, we'll have negative e to the negative infinity. Well, e to the negative infinity is 0, so this is just 0 minus negative e to the negative 1. So this is plus e to the negative 1, which equals 1 over e. And so we got convergence. So what we know is by comparison theorem on integral 1 to infinity e to the negative x dx, our integral converges. So now I want to look at how to use the comparison theorem on trig functions. So we're good here with continuity. Sine of x is a continuous function, so squaring it, it's still continuous. We're not dividing by 0 because 0 isn't in the interval from 1 to infinity. And our a value is 1, which is greater than 0. So we've already satisfied a lot of stuff. So the function is continuous because 0 isn't in the interval from 1 to infinity. Okay, now I need to find a comparison. So like I said, I like to look at the most difficult part, which I believe to be sine squared of x. What do we know about sine of x? We know that sine of x is greater than or equal to negative 1 and less than or equal to 1 for all values of x. So if I square this, this means that all of our negative values become positive. We'll still have 0 as possible because let's say we take like sine of pi, that would be 0. So sine squared of pi is still going to be 0. So this tells me that 0 is less than or equal to sine squared of x, which is less than or equal to 1. Now, if I divide everything by x to the 4th, I get that 0 over x to the 4th is less than or equal to sine squared of x over x to the 4th, which is less than or equal to 1 over x to the 4th. This is okay, I don't have to worry about flipping inequality signs because our x values are in the interval from 1 to infinity, which means I'm not dividing or multiplying by a negative number. Now, right away, I'm looking at this as my comparison function because it's greater than our given function, and I know by the p-test it converges. So let's go ahead and write this out. So this means that the integral from 1 to infinity sine squared of x over x to the fourth is less than dx is less than or equal to the integral from 1 to infinity of 1 over x to the fourth dx. So now we look at that integral, and we can immediately say by the p-test, it converges. And by it, I mean this integral. So then we got something that's greater than our given integral, and it converges. So then by the comparison theorem on integral 1 to infinity of 1 over x to the fourth dx, our integral converges. Okay, and this will be the end of improper integrals and the comparison theorem.